Hey everybody, today I'm going to introduce the T equation for independent samples. So in other words, this is when somebody in one group is not expected to have any influence on somebody's score in another group. So just those circumstances. So let's dive right in and take a look at this equation. Here's the T equation. It looks like a lot, but it's going to be just fine. In fact, most of this is already familiar to us. So let's go through this step by step. We'll get to understand it. Then we'll actually practice calculating with it in the next lesson. Okay, so as I said, we've already seen all of this, right? In fact, all of this should look very familiar if you just kind of avoid looking at the entire forest and start looking at the trees momentarily. As you can see, we've already seen this. This is a mean, right? We've seen the bar x. This is another mean. We've seen the sigmas, the sigma x's, right? All of this kind of stuff. So most of this is familiar. There's just a few things to keep in mind, so I'll pick those apart piece by piece just so that we're all on the same page. Okay, so one thing that we want to pay special attention to is the subscript here, right? As you can see here, here's a mean, and then here's a little 1 next to it, underneath it. So this is called subscript, and that's important. So we'll talk about that next. As you can see here, all of these little sub 1s, these subtext 1s, are important, and all of the subtext 2s are important as well. What that means is that we're getting this particular piece of information from the first group. Okay, once again, in an independent samples t-test, we have two groups that we're comparing on some dependent variable. So if we have two groups, we need to get information from group 1 and information from group 2. Now, it doesn't have to be a 1 and 2. You could call it whatever you want. You could call it group treatment and group control, or vice versa. It doesn't actually matter. We're just using the 1 and 2 to help us differentiate there. Okay, that's all that is. Another thing that we'll note here is these little n's, these lowercase italicized n's. Now, you'll recall a capital italicized n stands for something like the number of observations. The little lowercase n is APA format, the American Psychological Association's format, to indicate that this is a subset of the larger group. Okay, so in other words, if I were to include all of the observations of the variable, that would be a capital italicized n. If I have a lowercase italicized n, that is a subgroup of the entire group. And of course, I specify who it is by the little number there. So in other words, what I see right here is this is everybody who was in group 1, or the number of observations I had for group 1. And this little guy is the number of observations I had for group 2. Okay, very straightforward, no big deal. Now let's talk about the equation conceptually and what it's actually doing in principle. Okay, a very broad overview of this, of course, shows us that it is a fraction. In other words, we've got the numerator up here, then the denominator, which is much more complex down here. And that's fine, we're going to get to all that. Now this is important because that means that the t value that we're eventually going to have is a ratio of what's up here to what's down there. And so therefore it's very important to understand what is up here and what we're actually talking about. So as we can see, what we're doing is taking the mean of group 2 and subtracting it from the mean of group 1. Okay. Another really important way to think about this is subtraction is really just saying what is the difference between these two things that you're subtracting, right? And that's exactly what is in the numerator. It's saying what is the difference between group 1's mean and group 2's mean. Now, a really quick note here also is that remember in correlation, it didn't matter which variable we called x and which variable we called y. It didn't matter which one came first or second, except just kind of to keep it in track in your own mind. It does actually make a small difference in the t equation because, as you can see, if group 2's mean is larger, then you're going to end up than group 1's mean, then you're going to have a negative t value overall. It doesn't change the amount of difference between those two numbers, but it will change the sign. Okay. Now, that doesn't actually affect our interpretation at all, but it's just something to keep in mind when you get to the interpretation. So we'll talk about all that. So our numerator is just what's the difference between these two means. That's very easy. Now, of course, in the denominator, we have something much more complex, but if you take a very close look, actually this should look fairly familiar. If you just kind of ignore 1/2 for a moment, you'll look at this. We've got the sum of squares, and then we subtract the square of the sums divided by the total number of observations. That may look familiar from, of course, our standard deviation equation, because that is the standard deviation. In fact, this is quite literally just the standard deviations. Now over here you see this is all sub 1s, right? All of the subtext is 1. That means that we're taking the standard deviation from the group 1 observations. We're going to then add the standard deviation from the group 2 observations. Over here you can see these are all subtext 2's, meaning all of this information is coming from group 2. So that's all that is, really conceptually, is we're just adding the 2 standard deviations together, and this gives us something called the pooled standard deviation. Okay, that's something important, and we're going to come back to that because we'll use that for something special in the future. But for now, we don't need to worry about it very much. Just if in the future, if you're looking for the pooled standard deviation, you come to this point in your equation, whatever is in these brackets, you solve, you get to as simplified as possible. And then as you can see, you take the square root of that. That will give you the pooled standard deviation if that is all you need. However, as you can see, the square root operator extends beyond here. So when normally solving the t, we're going to include this. We're going to multiply whatever's here by this, then take the square root. So that's all fine. Don't worry about that. We'll talk about the pooled standard deviations more later. Now you can see over here, this is something that we have not encountered. It's not exactly conceptually difficult because this is just n sub 1, and we're just doing dividing by 1. So this is something called the reciprocal of the sample size, essentially. And then we're adding the 2 reciprocals of the sample sizes together. This is, of course, sample size of group 1, sample size of group 2. Okay. Now, conceptually, this is actually pretty straightforward what it's doing. If you think about what this would mean with the math, essentially what it does is it gives more weight to the standard deviation if you have fewer people in your groups or fewer observations of the variables. So in other words, the smaller your sample size, the more the standard deviation matters. It's going to have more of an impact on the value of the denominator. It's going to be larger. Therefore, if you want to reduce the sort of the uncertainty within your data set, then you can increase your sample size, and then mathematically what this does is it reduces the impact of the standard deviation in that denominator. So that's essentially it. The take-home message here is that you generally want to have more people in your study if it's possible, although that can be abused, but that's something we'll talk about when we get to statistical power later. So don't worry about that right now. But in summary, all this part is really doing is just increasing the impact of the standard deviation if you have smaller samples and reducing it if you have larger samples. So that's basically it. Okay, now in words, of course, this is very similar to what we've talked about before, is that what the equation is doing is taking the difference between the group means or the variation that we can account for with our independent variable. In other words, it's the variation in our dependent variable that we could account for in our independent variable, but then it divides that by the information that we cannot account for. It's because it's this dispersal of the scores, why the people in the samples were different regardless of our manipulation. Regardless of which group they were in, they differed from each other. And we don't know why. We have no idea why they differed from each other. That's just the way of things. That's just how it works. And so what the T equation does is it says how different were those group means compared to how different people were just generally on this dependent variable. And if it's a large group difference, and it gets to the point where it's proportionally large, not necessarily larger, but large enough that we can say it's not attributable just to how different they were. It's probably not an accident that we found different group means. That's when we start to say this is interesting. This is an interesting finding. There's something to this. Okay, that's something called statistical significance, which we'll cover in more detail later. This lecture just wants to look at the equation and become familiar with it in principle. So what we end up with is a t-value. A t-value in this particular case is an index of this ratio. In other words, it tells us an idea of the ratio between the variance we can account for and the variance we can't account for. And that is statistics in a nutshell, essentially, right? Okay, so next we're going to work on actually solving a problem using some data that I'll make up. I'll give you a little scenario that we can run through the actual calculations of this, and then we'll work on interpretation of a t-value. I will see you then. Thank you.